I will start to introduce. Hello, good afternoon, or good evening, or good morning, everyone. I am Jianying Shang from China Agricultural University. And before we start today's lecture, I would like to take a moment to introduce our two journals. The first journal is Biochar Journal. As the first journal specially focused on the biochar, the journal Biochar covers multidisciplinary subjects of agronomy, environmental science, and material science. It is a fully OA journal, and the latest impact factor is 15.1, ranking number 1 in the category of soil science and number 11th in the category of environmental science. The journal thinkings seek to publish original research in the field of preparation and processing biochar and its multifunctional application, including bioenergy production, biochar-based material for environmental application, soil improvement, climate change, contaminated environmental remediation, water purification, new analytical techniques, contaminated environmental remediation, life cycle assessment, and importantly, rural and regional development, and so on. It devoted to serve as an initiative, efficient, and professional platform for researchers in the area of biochar around the world to deliver fundings from this rapidly expanding field of science. Welcome to submit manuscripts to our journal, and we will appreciate for your attention, download, and academic citation. And also, I will introduce the second journal, Carbon Research. The Journal of Carbon Research is an international multidisciplinary platform for communication advances in fundamental and applied research on natural and engineering carbon materials, and that are associated with ecological and environmental functions, energy generation, and global change. It is a fully open access journal. The journal seeks to publish original research articles, reviews, rapid communications, comments, and perspective papers. It is dedicated to serve as an initiative efficient and professional platform for researchers in the field of carbon functions around the world to deliver fundings from this rapid expanding field. Carbon research covers research on carbon in associating with environmental science, renewable energy, and so on. Carbon research is served by a renowned, dedicated international editorial board in carbon research. Carbon research has high visibility for your work for free APC and open access. Now I will introduce our today's speaker, Professor Stephen Joseph. Professor Joseph is a visiting professor in the School of Material Science and Engineering at the University of New South Wales in Australia. He is a world-renowned authority on biochar and a pioneering figure in the field. He was one of the principal founders of the International Biochar Initiative. His research focuses on the thermochemical conversion of biomass waste into biochar and its application in agriculture, environmental remediation, and carbon sequestration. Professor Joseph has been awarded the Member of the Order of Australia for his contribution to environmental science and sustainable agriculture. He is also consistently ranked among the top 1% of the most cited researchers globally, reflecting the significant impact of his work. And also, he is he is an old friend of mine. He also gives a lot of help over the past several years. His support has been vital to our research. I really want to take this opportunity to thank him once again for everything he did for us. And today, his topic is renew and synthesis of 30 years of biochar research and development. And let's move this host to the Stephen.
Thank you very much for asking me to give this presentation. And Jianying is one of my very close friends and collaborators. She does amazing work. She and her team are really leading some of the most important research in biochar in the world. Okay, we're a bit behind, so I'm going to start. I've just got to get rid of this. Okay. A large part of my research I've published in a book for farmers. It's a farmer's guide. You can download it from the web. There's a small fee, but not very much. I want to, oh no, why is it? Okay. Yeah, okay. I want to start off with the early work that was done on terra preta soils. And I guess this was, for me, this was really the start of our deep dive into how biochar works and when it doesn't work. And I was really surprised when I first started looking at these dark earth soils, because people had talked about biochar as being charcoal. And when you look at the dark earth soils of the Amazon, they're very, very complex. And this is my favorite slide. Basically, it's a particle that looks black, but when you actually mount it and section it and look under the electron microscope, what you find is very small pieces of, let's call them biochar. They're high carbon particles, and they're surrounded by nanoparticulate minerals that are all bound together by organic matter. And there's many different sorts of minerals. What was very surprising is when we did detailed characterization, we found that these particles are super paramagnetic and they're highly redox active, and they contain a considerable amount of all of the macro and micronutrients. And so we started thinking, well, is biochar charcoal, or is it something more complicated? Or is when you put biochar into the soil, does it produce these, what I call biochar organomineral complexes? My background's in material science and chemical engineering, and I thought, well, this is a lifetime's work. When I started this, I was 50. I'm now nearly 76, and I still have much more research to do. Okay, so the other interesting thing that we found is that biochar is not a new technology. It's been produced by indigenous people all around the world. I just put this slide up. This is a slide from a village in the hills in Nepal. I had the privilege of being part of an Asia Development Bank team looking at the feasibility of biochar for Nepal. And we went up to this village, and the Nepali soil scientists and I asked this woman, does she use biochar? And not only does she use it, she makes it herself. So that was very interesting because she makes it with straw and dung, and then she builds a very simple earth mound and lights it and covers the biomass with the soil, and then she allows it to produce biochar over 4 or 6 hours. And then once she's actually made the biochar, she mixes the biochar with the soil and takes it to her fields. So one of the things that came out of this is traditional people just don't use straight charcoal. They use a mixture of charcoal and minerals and soil. So let's move on from looking at indigenous processes to what's happened with biochar research around the world. And one of the things we did was in the publication, The Farmer's Guide, was to try and put all of the meta-analyses together, mainly based on the work that was done at Cornell University, but also at Griffith University with Shala Hazani Bai. And what we found is that
Best
biochar
photos.
produced from crop straw manures, biosolids.
I should be one.
Sorry? Biochars are made from biosolids with low heavy metal content or wood that have been pyrolyzed with minerals and then pyrolyzed gave the greatest yields. The other surprising thing is that biochar produced at low temperatures, less than 400, gave the greatest yields over the range of crops that have been tested. When we started looking at soils, we found that low nutrient P absorbing acid soils and sandy soils were the most effective in terms of improving yields when you added biochar. The other area that was very interesting was that where you put the biochar was as important as the amount of biochar you put in and the type of biochar that you had. Okay, so that's sort of a general overview of what the research in fields was saying. And then we started looking at, well, why does biochar work, and especially biochar with high mineral contents and at low temperature? And one of the things that came out of all of this work is that biochar is basically acts as a geobattery. And in fact, as I'll talk about later on, it's not only a geobattery, it's a microbial fuel cell. And that when you put biochar, especially in the rhizosphere, what happens is that you change both the pH and also the EH. The EH is the electron activity. And that does a whole range of really interesting things to both the soil and the plant and the communities of microorganisms. I just wanted to highlight the little sketch that I did down the bottom, is that when we actually put some electrodes in the soil that has no biochar, and then we put an electrode in the soil that has biochar, we find that there's a potential difference. And so biochar can actually donate electrons, and it can actually accept electrons, and it depends on the state of the soil and its interaction with the microbes and the plants. The other thing we started noting is that biochar is involved in the production and the scavenging of reactive oxygen species. And the sorts of reactions that take place are highly complicated. They involve minerals that have a number of oxidation states. They involve certain microorganisms. And it's really important to understand that biochar has persistent free radicals, and those free radicals can be involved in all sorts of redox reactions within the soil. Okay. So in 2015, we published a paper called Shifting Paradigms. And what was quite apparent is that biochar is highly heterogeneous, and that the range of reactions that can take place on the surface of the biochar and in the pores of the biochar is quite amazing. They're both chemical reactions and they're biotic reactions. And what we noticed is that there's a big difference between the bottom of the pores, which are basically anoxic, and of course the biochar surface, where in most soils, except maybe in rice, they're oxic. And when you start looking at the biochar using micron scale electrochemical methods, we start to see that throughout the biochar there are different voltages. And those different voltages can result in different sorts of redox reactions. But it's not only the fact that biochar has a range of um, uh, microsites that are basically batteries. It's also the fact that the water in the pores of the biochar can basically stimulate a whole range of reactions. And all of these complex reactions seem to be responsible for biochar's ability to fix nitrogen and carbon. And one of the things that we think now is that biochar itself has an ability to increase soil organic carbon through both biotic and abiotic reactions. When I get time, I'm going to put together a range of very experienced people, and we'll try and actually detail all of the potential reactions that take place on the surfaces and in the pores of biochar. These are a set of micrographs that I show my students all the time. When you actually put biochar in the rhizosphere, the roots and the root hairs will interact, and they interact in complex ways. One of the things that we found very early on in our research work is that biochar increases the root colonization of avascular mycorrhizal fungi. And these mycorrhizal fungi live inside the roots, they come out and they actually go inside the biochar and they mine the nutrients that are in the pores of the biochar. But recently at Nanjing Agricultural University, we did some very complex measurements where we put a microelectrode inside the root and a microelectrode outside of the root, and we measured the root membrane potential. And what we found is that biochar increases the root membrane potential. And what that means is that it actually reduces the amount of energy a plant has to expend to take up nutrients. We also found that by loading the rhizosphere with nutrient-rich biochar, especially nutrient-rich biochar that had magnetic iron, we actually found an increase in endophytes, and we also found an increase in iron nanoparticles inside the cells. And in fact, we looked like they might have even gone inside the mitochondria. So this started giving me all sorts of ideas. If we go back to what I said about terra preta soils, we found that the terra preta particles had a high concentration of magnetic micron-sized and nanoparticles of iron oxide, and these iron oxide particles were magnetic. So I'm starting to think, well, why is biochar having such a big difference in a plant's ability to take up nutrients? And we think one of the reasons is that when biochar starts breaking down, these nanoparticles actually are liberated from the biochar, and they affect the size and the shape of the ion membranes, the ion channels on the epidermal layer. I'm not going to go into that, I don't have time, but it's fascinating. It's just such a complex set of changes that especially these mineral-rich biochars have in the rhizosphere. Okay, one of the early papers that a group of us, Johannes Lehmann, Martha Kamps, Lucas van Zwieten, did was to actually look at how biochar ages in soil. So we know that terra preta particles are basically 600 years old or thereabouts. So what happens from the time you put a piece of biochar in the soil to the time it becomes a biochar organomineral complex? And in a paper that we published 7 or 8 years ago, we showed how these changes occur. Essentially, when you put biochar into soil, the first thing you start getting dissolution of the readily soluble organic and inorganic components of the biochar. And once this has happened, you start getting fungi and bacteria growing inside the biochar, and you start seeing the biochar absorbing soil organic matter and soil mineral matter, especially on the surface. And what we find is that you start seeing these micro aggregates forming on the surface of the biochar, and you start finding very, very fine layers of organic matter inside the pores of the biochar. And over a period of time, you can't actually see the biochar pores anymore because they're covered in these micro aggregates, and they're covered in bacteria and fungi. And through perturbations in the soil and interactions with microbes and root hairs, we actually see that these micro aggregates are actually breaking off from the biochar and going into the macro aggregate structure of the soil. Okay, so what happens to biochar in terms of its effects on yield increases? And this is just a summary of two meta-analyses from Yi and Shala Hussaini Bai. It's in the Farmer's Guide. And you can see biochar added with fertilizer can increase average crop yields by about 42% compared to an unfertilized treatment, and can increase yields by about 22% compared to a fertilization alone. Biochar applied with fertilizer can increase average yields by 15% compared to a fertilized control. And low temperature biochars made from manure and crop residues give higher yield benefits than low temperature biochar. So that's basically, I think there's about 500 papers in those meta-analyses, but that sort of trend is, we keep on seeing it. And this is over a range of application rates. I just wanted to mention that a little bit about wood vinegar. I don't have enough time to talk about the large amount of research work that's been done on wood vinegar. But one of the things that we found is that if you add wood vinegar to biochar, it actually enhances its ability to both increase plant health and increase yield. A number of really interesting papers on this. And the other thing I wanted to mention is that the ability of biochar to increase yield seems to improve from year 1 to year 2 in a non-fertilized control, and in year 3 of a fertilized control. So the whole of the aging process seems to improve the properties of the biochar. And that's one of the reasons why I wanted to talk about aging before I came into looking at crop yields. Okay, I want to talk a little bit about how biochar builds up stable carbon. And there's been a range of papers published over the last 10 years. And one of the things that comes out of this is that if you really want to build up soil carbon, you need to add biochar on a regular basis. That adding a one-off amount of biochar can increase soil carbon, but you get a much more effective build-up in biochar if you add it on a regular basis. And one of the things that we know is that the biochar, after a while, will be taken into the macro aggregate structure of the soil. And over a period of time that you keep on adding biochar, you're going to start to produce the dark earths that we see in terra preta soils. And it's really important that if we're going to start having an impact on climate change, is that biochar must be added in the rhizosphere on a continuous basis. And we need to be careful about how much biochar we add, because if you add too much biochar in the rhizosphere, you can actually cause a decrease in the yield of plants. Okay, this is some work that I was involved in doing with Jianying Shang. It's some fantastic work that her students have been doing, looking at changes in inorganic carbon. And where you have calcareous soils and you have irrigation, one of the things that we found was that biochar acts as a catalyst to actually cause the calcium that's dissolved in the water to precipitate out for calcium carbonate and also the magnesium. And so biochar can not only increase soil organic matter, it can increase soil inorganic matter. I just wanted to mention briefly about biochar's ability to remediate land that has high levels of toxic metals and organic molecules, especially PFAS. I don't have enough time to talk about the exciting work that's happening with biochar and PFAS removal, but the important thing to note is, one, the ability to actually bind these toxic organic and inorganic compounds is complex, but what we do know is that once they're absorbed into the biochar, we start to see that these toxic compounds are then actually bound into the biochar through this aging process where organic matter and mineral matter precipitate out onto the biochar. And then as the biochar ages, the heavy metals will be locked up in these microaggregates. And we've talked about this in a number of papers, but it's really important to understand from a biochar standards point of view that even biosolids that might have a high level of especially zinc and copper are not necessarily toxic to plants, because when they're put into soil, the aging process will actually lock these heavy metals up. And it's a debate that is going on between the biochar industry and the regulators. It's interesting, we're just about to publish the first draft of the Australian Standard for Biochar. And one of the things that we've been able to convince our regulators is that biochar, you need to assess biochar not on its total level of PAHs and dioxins and furans and lead and chromium. You need to be able to look at what it does to the soil when you put the biochar in it. Does it increase the available toxicity in the soil? And if so, how long before it has an impact on the food that you have to that you will harvest and then, of course, eat? Okay, another one of my passions is feeding biochar to animals. In Australia, one of the biggest markets for biochar is in the animal industry. We've done a lot of research looking at the benefits of biochar. We know that it increases farmer productivity and animal health. But more importantly, if you feed biochar to animals that are out on the field, and especially if those fields have dung beetles, you can dramatically increase the productivity of your pasta over a 3-year period. The role of dung beetles is really important in taking this biochar that's in the dung into the soil surface. So you can also increase soil carbon as well as pasture productivity. I don't have time to talk about the non-soil applications, but we're now seeing a lot of research work looking at biochar in roads, in concrete structures, in packaging, in cosmetics, in pigments and dyes, in energy systems, as well as in water filtration and soil remediation. Okay, coming back to what I said about Terra Preta is not just straight biochar, it's biochar organomineral complexes. I think if you look at the research that's going on now, some people call them engineered biochars, some people call them biochar mineral complexes or biochar mineral composites. But what we found now is that if you enhance biochar either through copyrolysis or post-treatment, or both copyrolysis and post-treatment, you can actually improve the performance of the biochar and reduce the amount of biochar that has to be added to soil to give an increase in crop yields and in soil health and even in soil priming. Again, I don't have enough time to do all of this. One of the interesting new areas is that we found that by adding oxygen to biochar, that in itself has a significant impact on the plant's ability to take up nutrients. Very interesting work looking at actually putting nanobubble oxygen into biochar or treating it with hydrogen peroxide. I just really want to talk about the most exciting part of the biochar research and development that I've been involved in. And this is replacing all or part of a chemical fertilizer with a high nutrient-rich biochar. We did some very early work in China. It started off with the Bamboo Research Institute back in 2010, and then at Nanjing Agricultural University. And what we found is that if you mixed especially crop residues with minerals, especially clay and chemicals, that you could produce what we call a biochar compound fertilizer, which can both improve yields, reduce the amount of emissions, and reduce the amount of leaching. Now, the important thing to understand is that some crop residues work better than other crop residues. I've just given you some of the data we found. But the surprising thing is that you can apply very small amounts of biochar, between 80 kilos a hectare to 500 kilos a hectare, and you can get a very large increase in crop productivity. We actually found that we could get up to 30% increase in yield by adding 80 kilograms a hectare of biochar with a mixture of superphosphate and urea and diammonium phosphate. The other thing that there's been a lot of research on is what I call single mineral copyrolysis, where you have a soil that has a soil constraint. Let's say you have a cracking soil, and farmer practice is to add gypsum. So we did some work in Australia where we have a lot of very poor soils. We made a gypsum biochar composite by adding gypsum to the biomass before pyrolysis. And we added that along with the chemical fertilizers at 2.5 tons a hectare. And what we found is that the yield of broccolini was double. I mean, we were really surprised. how well this biochar composite could actually basically improve the soil structure, which led to greater nutrient uptake efficiency, which led to greater yields of the broccolini. Similarly, we've been looking at broadacre, where we've been making both a liquid application of this biochar gypsum compound as well as a solid product. And you can see here with the liquid product, we were getting a 67 increase in grain yield. This is in our soils in the south of Australia. So we've looked at adding diatomaceous earth, iron sulfate, magnetite, hematite to make magnetic biochars. One of the exciting areas we've been adding magnesium oxide, dioxide, calcium dioxide to biomass and pyrolyzing that. And we're fairly certain now that these co-pyrolysis processes with an oxide can significantly reduce methane emissions, both in soils and in animals. We need to do some more work, but I think this is a very exciting research finding that's going to be published very soon. A lot of work mixing clay with biochar that can increase cation exchange capacity, but more importantly, it actually increases the stability of the biochar, as well as when you mix that with NPK fertilizers, it actually slows the release and reduces the emissions. Again, we've done work with zeolites, lime, rock phosphate, and basalt. I don't have a lot of time to discuss this, but there's a lot of information that's being published now on the co-pyrolysis with these minerals. Commercially, there's a number of companies now that are making multi-component biochar mineral complexes. They're getting extremely good results on farmer-led trials. If people are interested, please come and talk to me, and I can tell you some of the exciting things that we're seeing in the field. This is an early trial we did, just to give you an example. We mixed wheat straw, poultry litter, bentonite, iron-bearing kaolinite, some basalt dust, and some wheat straw ash. A lot of work being done now, mixing ash with biomass and pyrolyzing, and that seems to enhance the properties of the biochar. What we did is that we did a field trial with seed potatoes, and we replaced different amounts of the NPK fertilizer with these biochar mineral complex, and we had a look at what happened to the yield of the seed potatoes. And what we found is that we got the greatest yield increase at a 20% replacement, but in terms of the saleable seed potatoes that have a weight between 120 to 250 grams, the application of 10% biochar replacement gave the greatest yield of saleable seed potatoes. So one of the things that I have to emphasize is that when you make these biochar mineral complexes and biochar compound fertilizers, there is an optimum ratio of the biochar to the NPK, and there is an optimum application rate, and you need to find out these by experimentation. Quickly talking about some of the work we're doing on making liquid nanoparticulate biochar fertilizers. This is some field pasture trials we've done. The picture on the left there shows that the roots are actually covered in this biochar. These are liquid fertilizers that are made from different biochars and biochar mineral complexes. And again, we found that the yield increases very much are a function of the age of the biochar and the amount of water. We've published some of this work. There's a few more papers we've got to do. The other area that we've been looking at is using biochar mineral complexes in trenches to try and stabilize soil, organic matter, and to increase water holding capacity of soils. The papers are out there. If people are interested, I can send it to them. Just out of interest, we've published this work, but one of the things we found is that you need to be very cognizant of the fact that the farmer needs to make a return on their investment. And there is a certain application rate of these biochar organomineral complexes that will give the farmer the greatest return on their investment. And you need to look at it whether you can just add these biochar organomineral complexes or whether you need to add them with fertilizers. This is a fairly complex set of numbers here. I don't have time to go through them all. But what we found is that this biochar mineral complex that we made that was a liquid, we could apply it at 700 kilos a hectare, and that gave the farmer the greatest benefit cost ratio. Some very recent work that's going on is to developing AI tools for farmers. I've been working with Griffith University on this. We call it Biochar Recommendation and Advisory for Crop Enhancement. We're at the beta stage. If people are interested in testing out our AI, please contact us. We've given, I think, probably 20 people have tested it, and we've had great feedback. But I think one of the things that we need to develop is these AI tools for farmers and for producers, so that for a given soil and a given biochar and a given fertilization regime, the farmers have a tool that allows them to maybe not get the optimum application rate and the optimum formulation, but certainly give them a much better start, because the AI has been able to interrogate all the many papers that have been published. Another area that we're doing research on is using biochar and these biochar trenches to capture and store water in photovoltaic farms. Fascinating work done by Deakin University and their PV farm. They found that these trenches were very good at capturing water in a very dry area in Australia. And more importantly, that the yield of the pasture was much greater, and the sheep preferred to actually come and graze in the areas where the biochar had been applied in the trenches. And also we applied biochar as a liquid on the pasture to get early growth. Other people have done work looking at actually growing crops under the photovoltaics. This is a schematic of a garden that we hope to build in Yixing at a company that I've been working with, is to incorporate PVs and biochar growth. Sorry, I've just had a mental block. They're basically beds that have trenches on the side of the bed that capture the water. Hopefully we'll get this built in the next 3 or 4 months. That's my talk. I've probably been a bit over time.